So at this point, you should have worked through this set of problems on gas laws. And so let's go over them now. So we're starting here with just a fairly straightforward unit conversion question, where we have the barometric pressure was measured, and we want to convert it into atmospheres. But you'll notice I gave it to you here in a slightly different unit. We talked about millimeters of mercury, and we know that 760 millimeters of mercury is equal to 1 atmosphere. But now I've given it to you in centimeters. Well, it doesn't really change the problem, it just means we have an extra conversion. We're going to need to convert from centimeters into millimeters. So we have 10 millimeters for each centimeter. So that gives us 742 millimeters of mercury. And then we can use that to convert to atmospheres. If we calculate that, we get 0.976 atmospheres. All right, in question 2, probably the most important thing to do is to figure out what's changing and what's staying constant. So we can see here very clearly the temperature is remaining constant. So the pressure is changing, and I've given it to you in torr in both cases, and the volume is changing. So we don't have any conversions we have to do. All we have to do is set this up using Boyle's law. P1V1 equals P2V2. So 6.414 liters times 850 torr is equal to the new pressure, 4423 torr times V2. Given that our pressure is going up, and up fairly significantly, we know our volume should therefore be going down. And if we solve for V2, we get 1.233 liters. All right, question 3. Let's see what we have. We have a volume of 1.425 liters. We have a temperature of 25.40 degrees Celsius, and we know we have to convert that to Kelvin, so let's just go ahead and do that. Again, we convert Celsius to Kelvin by adding 273.15. And we have a pressure of 583 torr. Now, what are our new conditions? So the second half of the question asks what volume, or the question asks what volume in liters. So we already know that V2 is unknown. Would this sample occupy at STP? So STP means that we are at 0 degrees Celsius, which again will convert to Kelvin, and 1 atmosphere. And that is the definition of STP, standard temperature and pressure. So our volume we don't need to do anything with because we want to get the answer in liters, and we're in liters for V1. That means V2 will come out in liters. we went ahead and we converted both of our temperatures to Kelvin. And then what about pressure? Well, with pressure, we have one of them in torr and one in atmospheres. And so the easiest thing to do will be to just convert this one into torr as well, because we know that 1 atmosphere is 760 torr. Now, can we make any sort of guess as to what's going to happen to the volume? Well, we can see our temperature is going down. If the temperature goes down, that means the volume should also go down. Our pressure is going up. When the pressure goes up, that means the volume should also go down. So if we do our calculation correctly, and we're going to use our combined gas law here, P1V1 over T1 equals P2V2 over T2. While we don't know what V2 is, we know it's going to decrease. And so if we get an answer that's higher than 1.425 liters, then we've done something wrong. So now we just plug our values in and we solve for V2. And we get a value of V2 is equal to 1 liter. So as we expected, it has gone down. All right, what about question 4? So this one is very similar to the one we did as practice in the previous video. But here now, instead of going to Pluto, we're going to go to Venus. And so our initial pressure is 760 millimeters of mercury. Now I'm going to convert that to 1 atmosphere because I can already see in the problem that our P2, which is going to be on Venus, is in atmospheres. And the reason I'm choosing to go that direction is it's just an easier conversion. Our V1 is 22.4 liters. V2 is unknown. Our temperature on Earth is 0 degrees Celsius, which we need to convert to Kelvin. Our temperature on Venus is 864 degrees Fahrenheit. So we need to convert that first to Celsius and then to Kelvin. Once we do that, we get 735 Kelvin. So now we can plug these into our gas law equation. Now, what's the expectation with volume? Well, the pressure has gone up. That should drive the volume down. The temperature has gone up though, and that drives the volume up. So we won't necessarily be able to make an easy prediction, but if we solve for V2, we find that it has gone way down, in fact, well below 1 liter. All right, our last practice question here. We can see that a container holds 50 milliliters of nitrogen. So our initial volume is 50 milliliters. And we want to know what will be the new volume if we increase the temperature. So V2 is unknown. T1, our initial temperature, is 25 degrees Celsius. As always, we have to convert that to Kelvin. T2, be careful here, because T2 is not 35 degrees. What we said is that the temperature is increasing by 35 degrees. So T2 is actually 335.15 Kelvin. Our pressure is 736 millimeters of mercury. What's our new pressure? Well, notice the question doesn't say anything about changing pressure, so we assume that the pressure stays constant. So now you can approach the rest of this problem in one of two ways. You can do it as a combined gas law question. But you know that P1 and P2 are equal. And so that means P1 and P2 will cancel. And so you're left with P1 over T1 equals P2 over T2. And then you can plug your values in from up above. I'm sorry, not P1. But that's V1 and V2 because the pressure is constant. If you plug in your values, we solve for V2. Given that the temperature has gone up, the volume should also go up. All right, so that's our practice on our first few gas laws. And now we'll pick up in the next video, looking at the ideal gas law.